Hey everyone, welcome back to another explainer. I am so excited you're here today because we're going to unpack something that is honestly absolutely fascinating, but kind of gets overlooked. We're talking about the magic of spatial representation in engineering and architecture. I mean, think about it for a second. How do we take the massive, boundless physical world around us, or, the invisible microscopic world, and translate all of that into something we can literally hold in our hands, study, and actually build from? Well, it all boils down to one thing: mastering scale.
Seriously, how in the world do engineers fit a tiny, microscopic gear for a Swiss watch and a massive, towering skyscraper onto the exact same standardized piece of paper? Without a solid system, it'd just be pure chaos, right? Imagine having to draw a skyscraper on a piece of paper the size of, well, an actual skyscraper. But thanks to the brilliant standardized language of scaling, we can basically manipulate our viewing lens to be as expansive or as highly focused as we need it to be. And the best part, we do it without ever losing that mathematical accuracy.
Okay, let's dive into this. The secret sauce really lies right here in the Universal Reference Table for Recommended Scales. This document is basically the ultimate translation guide for draftsmen all over the globe. Notice how elegantly it's broken down? Over on the left, we've got our overarching categories: enlarged scales, full size, and reduced scales. And right next to them, we have the specific, mathematically precise recommended ratios that fall under each of those banners. Today, we're going to decode every single layer of the standardization so you understand exactly how to interpret and apply these numbers. To really get this, we've got to start right in the middle with our first concept, the full size baseline. So this anchor point is what we call full size, and mathematically, it's represented by that 1-to-1 ratio, 1 to 1. This is our grounded reality. It basically means 1 unit of measurement on the page equals precisely 1 unit on the actual physical manufactured part. So an inch on the drawing is an inch out in the real world. It's the ultimate perfect match. But what happens when things get really small? Let's move to and see how this builds as we tackle zooming in enlarged scales.
Check out this absolute extreme from the enlarged category, 50 to 1. That is wild. We are literally blowing up a tiny object so the drawing on the paper is 50 times larger than it actually exists in reality. This is exactly how engineers can dictate those crazy microscopic tolerances with absolute clarity. It's exactly like taking a super powerful, calibrated magnifying glass and just dropping it right onto the page.
And as we look at this whole list of enlarged ratios, 50 to 1, 20 to 1, 10 to 1, all the way down to 2 to 1, you'll notice a very strict pattern. The larger number is always sitting right there on the left. That is your instant visual cue. The second you see a big number first, it screams, hey, this drawing is heavily magnified. It tells you right off the bat you're looking at an augmented, zoomed-in version of the real thing. Now let's flip that entirely. What about when a subject is just way too massive, like a bridge or a highway system? That's when we use zooming out reduced scales. All right, brace yourself for this one. 1 to 10,000. Think about that for a second. 10,000 units of sprawling, massive real-world terrain just squeezed down to be perfectly represented by a single unit of measurement on a standard page. Honestly, it's mind-blowing. You can take an entire physical landscape and plot it accurately and proportionally right there within the margins of a single sheet. Now, what's really interesting about this is the sheer volume of options we have available here. Look at these progressive intervals zooming out. We step down so cleanly from 1 to 2 to 1 to 5, 1 to 10, all the way down to that crazy 1 to 10,000. It gives architects and engineers this incredible flexibility to capture the exact right scope of any project. Whether you're mapping out just a single room at 1 to 50 or a whole city block at 1 to 1,000, there is a standardized ratio perfectly tailored for exactly what you need. So the crucial point is this. Enlarged scales lead with the larger number, while reduced scales lead with the 1. Simple as that. It's this beautiful binary system. That mathematical formatting tells you in a split second whether the drawing or the actual object is bigger. And because it's so universally standardized, a global workforce will literally never misread a technical document. And this brilliantly illustrates the unifying golden rule that unlocks the logic behind every single ratio we've talked about today. It is always, universally, drawing size on the left, real object size on the right. Always. Whether you're looking at 50 to 1, 1 to 1, or 1 to 10,000, that formula is totally unbreakable. The left side is always the paper, the right side is always reality. As we wrap up this explainer, I've got a quick challenge for you to test your new understanding.
Take a look around the room you're sitting in right now. Just look around. If I handed you a standard piece of drawing paper, what scale from our table would you actually need to pick to map out your space accurately? Would a 1 to 20 reduction cut it? Or, would you need to zoom out even further to 1 to 50? Think about the dimensions of your reality and how you'd shrink them down to fit right in your hands. It really kind of changes how you look at the spaces around you, doesn't it? Thanks so much for joining me on this deep dive. And hey, keep questioning the scale of your world.